It is my pleasure to introduce Harold and Dita, who are here to talk about GSM hacking, specifically running your own GSM network. So if you'll join me in giving them a round of applause, please.
Well, thanks for the introduction, and thanks for everyone to be here. It's definitely an interesting topic, and I was wishing to present on something like this for quite some time. Unfortunately, we didn't actually manage to get it done until now. So this talk is about how to run your own GSM network. And obviously the first question, well, not to many hackers, but to many other people, the first question is why? Right? So, why would you want to do that? Well, obviously for the same reason you want to run other networks. I still remember when I was like, I don't know, 12, and I bought my second PC, and I put the first Ethernet between those two systems. And sure, you can learn and you experiment with technology, you can understand how it works. Especially when we talk about the open source community, then to some extent, in this case, to boldly go where no man has gone before. For me, really, the underlying reason is that there are so many different security problems with GSM that people inside, well, let's say the IT security community are aware of, and which are theoretically documented or theoretically known. But nobody really can demonstrate these problems because, well, nobody who wants to demonstrate the problems operates a network. So this is a very important fact. I mean, for example, the number one problem with GSM is that the network authenticates the mobile device, but the mobile device does not authenticate the network. So anyone who comes up with a network and says, well, I am whatever kind of network, people will log into that network. And there's no way how they can determine whether they are on the legitimate network or on an illegitimate network. And this results in all kinds of other problems. And something like this has to be brought to the public attention. There are like literally billions of GSM users out there who have no clue about the insecurity. You know, they use this for payment systems that facilitate GSM. You know, for online banking where SMS is transported over GSM in some cases. For all kinds of applications where people typically assume confidentiality or privacy or whatever kind of other security features, which I believe nobody has ever indicated that they actually exist, or nobody ever stated that they were there. Anyway, so raise public awareness about the problems that are here. So a legal disclaimer, don't try this at home. GSM operates in the licensed spectrum, at least in, well, almost all parts of the world that I know of. So in order to operate your own GSM network, you need approval from the respective regulatory authority. So you, in fact, can only use the BTS with a dummy load, basically not transmitting any signal. And obviously, don't interfere with any operators. This will be a very unpleasant experience, I can assure you. I'm just having a very vivid imagination. So the software that we are talking about is, and this is really true, it is for research, right? I mean, we want to point out and demonstrate the problems that GSM has, and that's the reason the software is being developed. The software that we're talking about is mainly 2 programs, and those 2 programs will be released as open source later today. And there will be an according wiki and so on. So, we need to talk a little bit about GSM, because unfortunately, at least it's my experience, not many people know too much about the details, or, well, at least whatever, I mean, there's all kinds of details, but even the very, very high-level details, many people don't really know about GSM networks, which is, again, one of the reasons why we need this kind of technology in the hands of the people. if you look at the amount of security research that is being done on TCP/IP and the internet and so on, and you look at the amount of security research that's happening in mobile phone networks, then it's probably, I don't know, 1,000 to 1 ratio, if not more, maybe 10,000 to 1. And that's weird, you know, it shouldn't be like that. And so more people need to learn about GSM, and that's obviously easy with open source software and so on and so on. So unfortunately, there's no hitchhiker's guide to GSM networks, and the literature you can buy in form of books is typically either extremely low-level RF, which normally most people don't care, especially not people who deal with security, or it is extremely high level, more to the extent of how do I design a network, how do I deploy a network, how do I position the cells, and this kind of stuff, which is obviously not interesting as well. So then you have the protocol specifications, which are publicly available, which some people are surprised by that, but yes, you can get everything but the encryption documentation. It's 1,108 PDF files, 414 megabytes. I don't know how many pages. I wanted to implement a script that counts the pages in all the PDFs, but I didn't find time for doing that. But what I did is actually convert them all to text so I can grab them. Anyway, so the specs are out there, but it's really hard to get started. And this has been a process, at least for myself. I don't know how it is for Dieter, but I have been learning more and more about GSM throughout the last, I would say, 3 years or something like that. Not full time, right? It was just here and there, learning bits and pieces here and there, and after some time it starts to make sense. So if you look at the GSM network architecture, then it's like if you don't know about telecommunications networks, then it's very, very different than like if you just have a TCP/IP internet kind of background or Ethernet kind of background. It's a bit synchronous network, sort of fits into the entire telco industry's synchronous digital hierarchy, SDH. Has many analogies from ISDN. This is supposed to be SDH at the end, by the way, not SDN. The layer 2 is modeled after Q921, which is the layer 2 of ISDN. It has some extensions. The layer 3 call signaling, only the call signaling, which is only one particular small part of the entire GSM system, is modeled after Q931, which is the basis for example, the Euro ISDN protocol, which is spoken on ISDN systems all over Europe, at least. So there's all kinds of other protocols for management of radio resources and so on and so on. However, there's one thing that is, again, very similar to the traditional telecommunications network in a sense that the logic or the intelligence is built into the network, not so much in end-to-end. So if you come from an internet point of view, then you have all the entire protocol stack on both ends of the connection, and the network in the middle is very stupid. It just passes on packets. That's extremely different in GSM. I would call GDSM a TDMA nightmare. I've been working a bit on other projects as well for GSM protocol analysis, so just passive sniffing of GSM. And it's very, very hard to understand who sent some data or for whom data is sent at a given point in time without knowing tons of contexts and keeping very accurate timing and so on and so on. It's not just that there are like 8 time slots on a radio channel. That's very easy, no, but it's the multi-frames, hyperframes, and all the complex setups on top. Anyway, let's go on. So what do we have in a GSM network? We have a mobile station. We have a base transceiver station. It's important to say the base transceiver station because it really is a transceiver. It's not a base station. But if you say it's a base station and you think of something that actually can interact by itself with the mobile device, that's not the case. It's just a transceiver. You have a base station controller, which implements all the logic, a mobile switching center, and so on. I'm going to talk a little bit about what these individual parts do. So the BTS is the base transceiver station. It handles the layer 1 of the radio and parts of the layer 2 on the radio side. It handles obviously the modulation, demodulation. There's an RF power amplifier. There's VCOs and so on and so on. The time multiplex, the scheduling of frames, these kind of things are done by the base transceiver station. But as I said, it's not a self-contained base station. It doesn't do anything by itself. The base station controller has to tell it everything. Like base station controller has to indicate what kind of beacons to send. Base station controller has to decide at which power level to send which frame, and so on and so on. So it's a fairly stupid, in quotes, device that just has some kind of offload capability for the base station controller. The base station controller then does the actual decision making for most parts of the protocol. It controls almost all aspects of the base transceiver stations. And also handles a handover between different base stations in one base station controller. So you have one base transceiver, you have a number of base transceiver stations which are all connected to one base station controller. And if you roam between those base stations, or if you hand over between them, then the base station controller takes care. If you move to a base station that connects to a different base station controller, then the base station, the mobile switching center gets involved, which is the next element in the hierarchy. It handles switching of the actual calls. It does what's called, that's literally a term from the standards, interworking with ISDN, or the analog telephony systems, talks SS7. And then you have the home location and visitor location register, which has the database for the subscribers and so on and so on. So the interface between the base transceiver station and the base station controller, that is what we have been working on mostly. It's called ABIS. I have no idea what ABIS is supposed to mean. It's based, like the physical layer is an E1 line, S2M sometimes called in Germany at least, so 2 megabit synchronous link that exists in SDH. And it has a couple of protocols on top of that. It's layer 2 management, which is for TEI establishment. If somebody has dealt with ISDN before, you know TEIs. The organization maintenance layer and the radio subsystem layer. And basically you have one time slot on the E1 which has the actual control channel, and the other time slots then have speech data. I'm going to go a little bit more into detail. So the ISDN E1 interface basically has 32 time slots. One of them is CRC, so 31 are remaining, and on one of these 31 you talk the actual signaling, and 30 time slots remain for voice data. There's a particular encoding on the wire, but these are all details that we do not need to get into. And despite this diagram says that time slot 16 is usually carried for signaling, this is in ISDN. In the ABIS protocol on GSM, you can actually configure which time slot the signaling is running on. We are doing it on time slot 1, for example. So now for the speech and data traffic, I'm going to hand over to Dieter.
Okay, I will tell you something about how speech is encoded. We have basically, we have basically two different signaling streams. There is the signaling to the base station transceiver, which controls the ear interface, which goes to the mobile equipment. Then there is also some sort of operation and maintenance stream, which controls the base station itself. It tells it what frequency it shall use and such things. Those streams are controlling streams. They are only they are handled in packages, and a message is sent and tells the station do this or that, and it gets back a result. Speech is different on data traffic. It's transmitted all the time. If there is no speech, you receive some sort of idle frames. There's nothing inside. It just tells no speech going on. Speech traffic is handled in one of the time slots we have in the ISDN channels, and you can configure the time slot which is used for transferring speech or traffic. Speech is the speech and